there, chemistry. This is a mystery arc drawn on the page, and I haven't even started yet. All right. Um, excuse me, this is podcast 7.2, where we're going to talk about phases of matter. All right, so we've got solid, liquid, and gas states, right? Okay, so both liquids and gases, we know that solids have a definite shape and a definite volume. Liquids have an indefinite shape but a definite volume, and gases are indefinite shape and indefinite volume, which means that the liquids and the gases take the shapes of their containers. Solids do not. Gases have an indefinite volume, which means that they're going to expand to fill their containers, but liquids do not. And the question is, why? All right, well, let's talk about why. The reason they don't is because of these things called intermolecular forces. Okay, intermolecular forces are things that are like electrical charges or forces that pull these things together. It's like attraction. So, like opposite charges that kind of stick together, and that's why the liquid molecules and the solids stay together, because the bond in them is a lot stronger. Whereas in gases, there's enough kinetic energy in the gases that they can overcome the force of attraction, and so they're able to bounce all over the place. Okay, so what's the difference between the three? Well, in gases, there's complete and total chaos. It's disorder, like there's no tomorrow. It's like well, that's not good. We don't want to see that. Sorry. Okay. So it's as if, think about it this way. You give a bunch of 5-year-olds who have had no nap a bag of candy, and you let them eat all of it. Okay, that's a gas. They're crazy. They're running all over the place. They're going in a straight line until they hit something and bounce off it and go in a different direction. Okay, that's a gas. Liquids are kind of like teenagers. They know how to sit still. They still kind of move around a little, but they know how to stay in their own little place, right? And then a solid, arranged, nice, neat, those are adults. We kind of just stay where we're supposed to be, right? Makes sense now. Okay, solids, liquids, and gases. Okay, so what are the phase changes? Well, the phase changes could be freezing. Now, freezing is when you go from something that's liquid to something that's solid. Okay, how do you do that? You do that by taking away energy. Energy is being released. It's being given off. So we would call that, and I know we haven't really talked about it too much, but if you're releasing energy, it's called an exothermic reaction. Exo meaning outside, thermic meaning heat. Okay, so outside heat is being released. Energy is released. If energy is being absorbed or taken in, we call that endothermic. Thermic again being heat, endo being inside or taking in. All right, so freezing would be an exothermic reaction or an exothermic change because it's releasing that energy so that it can go from a liquid state to a solid state. All right, when you condensate something, condensation is what happens when a water vapor changes into liquid. Okay, condensation is something that you see on your mirror when you get out of the shower and your mirror is all fogged up. Okay, fog is an example of condensation. That's when those water vapor molecules get condensed down, energy is released, and they change into water. All right, deposition. Deposition is a cool thing. Deposition is when water vapor goes directly to the solid phase. It doesn't even go to the liquid phase. It goes directly to the solid phase. Okay, that would be an example of deposition. Definitely an exothermic reaction. Heat is being given off. Dissolving. Okay, so dissolving would be from solid to liquid. Melting would be from solid to liquid, right? You're putting energy into both of those, and so you're increasing the kinetic energy of those molecules. Vaporizing or evaporating would be liquid to water vapor, so liquid to gas. You're putting energy in, so it's an endothermic reaction or change. And sublimation or subliming. Sublimation is from a solid to a gas, and that is what happens with carbon dioxide on dry ice. Okay, so it's going directly from a solid to a gas, and it's not passing through the liquid state at all. All right, so what happens when something boils? So you know that you put a pot on the stove to boil. All right, and most of the time, if you're going to make pasta, you put some salt in it for flavor, right? Wrong.
You don't put it in for flavor, okay? You actually put it in there because when you put the salt in, you're going to raise the boiling point of the now saltwater solution. And it's going to cook at a higher temperature. It's not for flavor. You add the flavor in later. Okay, that's a cooking tip. I'm not a cook. Well, I am, but not a professional one. All right, so let's talk about what happens on the scientific level with boiling. So what happens is, in order for something to boil, well, you got to add energy. So we increase the kinetic energy and we allow the liquid at the surface to change into a gas. Okay, so we've got the evaporation going on before it actually starts to heat up. As it evaporates and you add that additional kinetic energy, the bonds are going to break between the particles and those liquid molecules are going to start to change to the gas phase a little bit quicker. Okay, now we're just starting to see those teeny tiny bubbles that are at the bottom of the pot. It's not boiling yet. Liquid molecules are just changing to the gas phase. Okay, you're creating water vapor right above the surface of the liquid. Water vapor. Okay, do you want to put your hand there? Probably not. Okay, because you still have steam coming off, but you've got that water vapor just above the surface of the liquid. All right, when that water vapor pressure just above the surface of the liquid becomes equal with the atmospheric pressure, you're going to start seeing those big bubbles come up, and that's what we call boiling. Okay, the water vapor pressure has to be equal to the atmospheric pressure in order for something to boil, and that's what we would call boiling or boiling point. Okay, so what happens is that the liquid starts to evaporate. As the liquid evaporates, you add more kinetic energy, which breaks those bonds between the particles. The liquid molecules change into gas, creating water vapor just above the surface. The vapor pressure from the water just above the surface has to equal the atmospheric pressure, and the liquid will boil. It's probably something important. I just said it twice. Okay, moving on. All right, so we've talked about gases. We've talked a little bit about liquids. Let's talk about solids. All right, we've got two types of solids. You've got what we call a crystalline solid and an amorphous solid. Okay, crystalline solids are crystals. They're nice, they're neat. The particles, their atoms are all arranged nice and neat and orderly. They repeat. It's a pattern. It's what we call a lattice. Okay, these things have extremely high melting points. They maintain their own shape no matter what you do to them. They're usually going to be good conductors, and some examples of these would be table salt, granulated sugar, okay, copper 2 sulfate, things like that. All right, then your amorphous solids are going to be things that don't actually have a structure to them. They're bendable, they're moldable, they can be moved into different shapes, they melt over a wide range of temperatures, low and high. Poor conductors. Examples of these: powdered sugar, glass, plastic, and wax. Okay, just know the difference. Okay, phase diagram. So you're going to be working on this. This is based on the relationship between temperature and pressure of a substance. Okay, make sure that you pay attention to the axes of the graph. Typically, on this graph here, your y-graph, your y-axis, you're going to have pressure and you're going to have temperature here. If you have pressure on the y-axis and temperature on the x, then you should have a solid, a liquid, and a gas phase. Oh, that's all I did? Oh, what am I doing? Okay, so you have your solid, your liquid, and your gas phase. Solid to liquid would be melting. Liquid to solid would be freezing. This line right here that separates the two shows us where they are at equilibrium. Okay, so we would call that the melting point / boiling point line. Okay, what does that mean? Well, that means that if this substance is at 1 atmosphere, and I ask what temperature does it boil, what is its boiling point, you would come over until you reach the line for boiling point, and you would go down. Ooh, that was bad. And you would say, oh, well, the boiling point would be 0 degrees Celsius. Not boiling point, sorry. Melting and freezing. That would be freezing point. I am not with it right now. Okay? If we want to melt it, we've got to have it at 0 degrees Celsius to melt it. If we want to freeze it, the opposite direction, we have to have it at 0 degrees Celsius to freeze it, and then lower the temperature, right? Okay, well, this is liquid and this is gas. So this line right here shows us this is the melting point. Gosh. Redo. Can I rewind? Let's try this again. Okay, we want it to go from liquid to gas. So this is the boiling point. Oh my gosh, what am I doing? Okay, that's correct this time. I'm sorry.
All right, so if I wanted to know the boiling point of this substance at 1 atmosphere, you would come over until you hit that boiling point line, the line that changes from liquid to gas, and you go down and it boils at 100 degrees Celsius, and that's how you read this. Okay, this line right, this little dot right here, this is where all three phases can, the conditions for all three phases to coexist are prime. Okay, they're there. And so we would call that line right there, we call it the triple point. Okay, triple point. And that means that the conditions for all three phases to exist at the same time are favorable. Okay, triple point. This point right here, we call, oh, it's labeled, we call that the critical point. Okay, and what that means is that above this temperature, the line, or above this point, the line, the difference between liquid and gas, you can't tell the difference. So everything just looks like a gas. The line is just, it's so small, it's negligible, and so everything exists as a gas above that temperature, that critical point. Okay, I think we've covered everything here. Sublimation, deposition down here. Yeah, I think that's it. So you'll be using this right here and answering questions about it when you come into class. And that's it. So we'll see you then.